Hello, you all. This is Verily Berry Jr. back with some linear algebra. I last time went to column spaces and null spaces to get a better understanding of this chapter 4, section 1, inconsistent systems and projection. So now that I have a better understanding of that, I will continue with the chapter 4.1. And I'll actually just start again from the beginning and detail the specifics about the null space and column space and see if I have that down enough before we go into solving these systems. All right, so let's see what we have. All right, so it says projections and linear transformations. An inconsistent linear system has, of course, no solution. But we might try to do the best we can by solving instead the system Ax equals P, where P is close to B, but is inside the column space of A. All right, so let's look at the column space part. It's saying that Ax equals B is inconsistent, no solutions. But we can try to solve Ax equals P, where P is the vector closest to B, but lying in the column space of A. So if A equals these column vectors, then B then P equals A1 plus A2 plus A3. Or I guess I should say uh, alpha, beta, gamma, I guess I should say. It's some scalar, some linear combination of those parts. Because a column space is basically the vectors that solve to B. And I guess technically, and I'll go back to the four subspaces part. It says spanned by the column vectors. Yeah. And this is the example we did earlier. So you have to solve for 0 to get the null space. But the vectors themselves, he only mentions 3 because 2 of them repeat, span the column space. So the vectors, or the actual vectors of the matrix, excluding the duplicate 1, 1, 1, 1. And they span the column space. So P is some combination of these, and it might even be that beta and gamma are 0, so it's just some scalar of one of them. But P is in that column space. So that's why we're going to solve X for P instead of A. That makes sense. So P is basically the closest thing we can get within the column space, while B is not in the column space at all. Right? Let's continue. This naturally involves the notion of projection of vectors in Rn onto subspaces, which is our fundamental example of linear transformation. In this chapter, we continue the discussion initiated in Chapter 2 of linear transformations, the functions underlying matrices. We will see that a given linear transformation can be represented by quite different matrices, depending on the underlying basis or coordinate system for our vector space. A propitious choice of bases can lead to a more convenient matrix representation and a better understanding of the linear transformation itself. Right? So, example, suppose we have the system AX equals B. To solve, where A equals 2, 1, 0, 1, 1, 1, 1, negative 1, and B equals 2, 1, 1, negative 1. So first thing is, let's get the column space. So the column space of A equals span 2, 1, 0, 1, 1, 1, 1, negative 1. And the null space of A equals the solution to, to say x given ax equals 0. So we'll solve for that. We're imagining 0 on the right side. So we'll do like the textbook does and simply not write the zeros. Right? So we can say that swap these around. And these are 4 by 2 and 4 by 1. So that means that x has to be 2 by 1. And there we have it. We have x equals 0 and x2 equals 0. So the null space is really So the null space of A equals 0, 0. Let me make sure I have that right. The null space of A is the set of solutions of the homogeneous system AX equals B. So the null space of A is X in Rn, and it's definitely in Rn because n is 2, and this is a vector in R2. All x in R2 where x equals 0. For the x in R2 where ax equals 0 is x equals 0, 0. So that's the null space. So we have the null space, we have the column space. Let's go back to the example. The reader can check if B is in the column, as the reader can check, B is not in the column space of A. And that is true. 0, 0, I'm saying B is not in the column space of A. Yeah. So B equals 2, 1, 1, -1, and that is not in the column space of A. There's no way to scale B so that it equals either 1, 1, 1, -1 or 2, 1, 0, 1. And now the them are clearly that. So B is not in the column space of A. So we have that. Because this is the column space, except that the column was written as a span. So the system is inconsistent. If it was consistent, B would be in the column space of A. It seems reasonable instead to solve Ax equals P, where P is the vector in CA that is closest to B. So we want to find which one out of 2, 1, 0, 1 and 1, 1, -1 is closest to B. The vector P is characterized by the following lemma. So V is in Rm and is a subspace. So that means it has closure under 0, sum, and scaling. And B is in Rm, and P is in the space V. It has the property that B minus P is is perpendicular to the base, the subspace we're talking about. So B minus P, the magnitude of that, is less than B minus Q for all vectors Q and V. That is, if P is in V, and P differs from B by an element of perpendicular to P, then P is closer to B than every other point in B because it's connected by a normal line. And they make a good illustration of this. And I'll be very clear about this illustration here. So this is a plane that's also the vector space V. So the column space That must be why it says span. Because if I had a plane like x equals 121 t plus 242 s, we'll be able to make a matrix 121 242. But these matrices would really be the vectors that span this space. So the column space is all the points inside a vector, a vector space or a plane, for instance, or hyperplane. So this is our A. So this would be similar to saying that this is A, and you can pull the vectors out and make them linear combinations. This is what it seems they're saying. They started with a parametric and made it a matrix, and that sort of matrix ends up being the span. The column space of the matrix is the span of the space. So back to the example. So they have a triangle drawn. Hmm. Like so. And we have this as a right angle. And we can say we can say that P oh, click the broadening line by mistake. We could say P is here. We can say Q is here. And we can say B is here. And keep in mind that this side is on the plane. And perhaps it'd be better or more clear if I pull this down. So we could imagine that the plane is flatter and the triangle is sort of projecting up over the plane. And we can say that RM, I'm not sure why the RM is there except for the fact that the uh, first, as you can say, the row space of A is M, but the column space spans V. It's like in the example I did a moment ago. So so B minus P is perpendicular to V. B minus P. That's B minus P. And Q minus P is in V. So we'll call this Q minus P. And it's in the plane. So that means that vectors V minus P and Q minus P are orthogonal, form a right triangle, and hypotenuse is B minus Q. B minus Q equals hypotenuse. That's just this. Thus, by the Pythagorean theorem, the magnitude of B minus Q is going to always be greater than the magnitude of V minus P. The hypotenuse is always going to be longer than either side. So P is closer to B than every other point. All right? It makes sense. Than every other point in V. We'll be getting there. This makes sense. We have to put it in the context of the other things going on. So recall theorem 4.9 from chapter 3. Any subspace V, technically V, I guess, is not a plane, but it's a subspace. It's like it's cut out of a plane. In Rm and V in Rm, because the B in X equals B is going to have the same M value as the same row value as the matrix. There's a unique way to write B equals P plus B minus P, which is simply calling out this action here, P plus B minus B, P plus B minus P, and P is in the vector space, but B minus P is in the perpendicular to the vector space. Everything makes sense so far? So definition, V is a vector space in Rm, the rows is a subspace, meant to say, and B is in Rm. So the rows, the column space spans V. I'm still not putting my finger on the RM part, how that relates, how the RM relates to the subspace V. We define the projection of B onto V, which is going to be P. Projection of onto V of B equals P, which is going back to this illustration here. P is the projection of B onto the subspace. P is within the subspace with the property that B minus P is in the perpendicular to the subspace V. Thus, P equals the projection of B onto V. All right, with them so far, remark, since V perpendicular equals V, it follows that the projection of B onto the perpendicular is B. Projection of B onto the perpendicular is B minus P, which is B minus the projection of B onto V, which is B minus P. Okay? Let's write that down. So the projection onto the perpendicular to V by B, which means B is projected onto the yellow line there, equals B minus P, which is the yellow line there, B minus P, and that equals B minus the projection onto the vertical by B, because B projected onto the vertical is B minus P. Now, like I wrote the notation wrong though. It's projection of P is the projection of B onto the vertical. So if I on the vectors, the subspace. So if I project B down onto the subspace, it is P. So it's projection onto the subspace by B, not the perpendicular. The perpendicular on projection onto the perpendicular is B minus P, which is this right here, projection onto the perpendicular of B. And since B minus P, which is the yellow line there, is perpendicular to the space, and we can see that the yellow line is coming out of the space, then B minus B minus P, B minus B minus P is P, which is in the space itself, which is in the perpendicular to the perpendicular. So all that to say that B equals the projection onto V of B plus the projection onto V perpendicular of B. So basically what it's saying is B is the blue plus the yellow. The projection onto V of B and a projection onto V perpendicular of V of B. Simple enough. To calculate P explicitly, we proceed as follows. Now we're finding out what P is. Suppose V is n-dimensional and the vectors that span V are V1, V2, Vn, let's say. They span V. So that means we had a matrix. So let's say V span equals V1, right? So we see that the number of the vertical vector is the number of the column, and those span. So basically, X would be right. So they span the subspace. So they're the column space equals the column space of V. Consider the n by n matrix. And here m equals 3 and n equals, well, 3 as well, but you can see n. But we want AX equals P, where V minus P, which again is the yellow line, V minus P is in the perpendicular to the column space of A. So the column space of A spans V. So the perpendicular to that B minus P is there, which makes sense, which is the yellow line. So by theorem, 0.5. Oh, hold up. Let me get my stream working again. Naturally, perhaps it's a good time to take a break right now, actually. So I'll take a quick break and then we'll come back and pick up from there momentarily. So give me about 15 minutes and we'll start again.